Have you ever stopped and wondered what temperature really is? I mean, we all know what hot and cold feel like, but what's actually happening when a puddle freezes over or a kettle starts to scream? So come on, let's dive in and take a journey from our everyday feelings to the hidden scientific truth of what it means to be hot or cold.
In this explainer, first we're going to uncover why your own sense of touch can be a pretty terrible thermometer. Then, we'll shrink down to the atomic level to see the secret life of particles. We'll explore the three faces of water, learn how we build tools to measure heat objectively, and finally, see why temperature is just absolutely crucial in our world. All right, first up, a deceptive feeling. This is where we challenge what we think we know, because it turns out your own hands can be really easy to trick when it comes to temperature. So, let's get right to it. Can you really trust your hands to tell you how hot or cold something truly is? It seems like such a simple question, but the answer is, surprisingly, a definite no. And let's find out why with a quick little experiment.
You can actually try this at home. Get 3 bowls, one with cold water, one with warm, and a third with just room temperature water. Put one hand in the cold and the other in the warm. Let them sit for about 30 seconds. Now, plunge both hands into that middle room temperature bowl. What happens? The hand that was in the cold water feels warm, while the hand from the warm water feels cold, even though they're in the exact same water. So what in the world is going on? Well, here's the secret. Your body doesn't detect absolute temperature. It detects the flow of heat. For your cold hand, heat is flowing into it from the lukewarm water, so it registers as warm. For your warm hand, heat is flowing out of it, so it feels cold. This is the exact same reason a metal pole feels so much colder than a wooden bench on a chilly day. They're both the same temperature, but metal is a fantastic conductor, so it yanks heat away from your hand way faster.
So, if our senses are this unreliable, what is temperature, really? Well, to find out, we have to zoom in, like way in, to the secret life of the particles that make up everything around us.
Okay, scientifically speaking, temperature is a measure of the average kinetic energy of the atoms and molecules inside something. Now, kinetic energy sounds complicated, but it's not. It's just the energy of movement. Everything is made of these tiny, constantly moving particles. And temperature is really just a way of measuring how fast, on average, they're jiggling and bouncing around. Think of it like this. In a cold object, the particles are moving pretty sluggishly, just kind of vibrating gently in place. But in a hot object, oh man, they are zipping and ricocheting around like crazy. So you can think of temperature as a kind of molecular speedometer. The higher the reading on the dial, the faster those particles are moving. And that leads to a really fascinating question. If temperature is just motion, is there a point where everything just stops? And yes, there is. It's called absolute zero. At 0 on the Kelvin scale, all that particle motion would theoretically just cease. It is the ultimate cold, the absolute bottom of the temperature scale, a place colder than the deepest, darkest reaches of space. Okay, so particles jiggling faster means higher temperatures. Got it. But what are the real-world consequences of that? Well, let's explore this with an example we all know really well, water, and its 3 different faces. At 0 degrees Celsius, we hit water's freezing point. As we remove heat, the water molecules lose energy, and they slow down their chaotic little dance. Eventually, they're moving so slowly that they just lock together into a fixed crystalline pattern. Now they're still vibrating a little, but they can't roam around anymore. They've become a solid, ice.
Now let's go the other way. Let's crank up the heat. At 100 degrees Celsius, we reach the boiling point. Here, we've pumped in so much energy that the water molecules are moving incredibly fast. So fast that they violently break free from the bonds holding them together as a liquid and just escape into the air as a gas we call steam.
And here's where it gets really cool. On top of Mount Everest, water boils at just 69 degrees Celsius. So, why? It's because there's less air pressure from the atmosphere pushing down on the water's surface. This makes it so much easier for those energetic molecules to break free and escape into the wild as a gas.
So to just quickly recap these states of matter, in a solid, particles are locked in place. In a liquid, they can slide past one another, taking the shape of whatever container they're in. And in a gas, they just fly around freely, filling all the available space. It all comes down to the energy and motion of those tiny particles.
This brings us right back to our original problem. If our hands can't be trusted, how do we get an objective, reliable measurement of all this particle motion? For that, we need the right tools, and they're built on a really simple principle.
That principle is called thermal expansion. Remember how hotter particles move more and push each other apart? Well, that means as most things get hotter, they physically expand and take up more space. And we can harness this predictable behavior to measure temperature with amazing accuracy.
And here are two really clever ways we put that principle to work. In a classic liquid thermometer, a bit of colored alcohol in a bulb gets warmer, expands, and it's forced up a very narrow glass tube. In something like an old oven dial, you have a bimetallic thermometer. It's a strip made of two different metals bonded together. As it heats up, one metal expands more than the other, forcing the strip to bend or coil, which moves the pointer on the dial. Pretty smart.
Of course, a thermometer needs a scale to be useful. Celsius is cleverly based on water's freezing and boiling points, a very neat 0 to 100. Then there's Fahrenheit, which uses different reference points, where water freezes at 32 and boils at 212. And finally, there's Kelvin, the scale scientists prefer, because it starts at the coldest possible temperature, absolute 0.
So after all of this, why should we really care? Why does measuring the jiggling of tiny, invisible particles matter so much? Because, well, it's the bridge that connects that microscopic world to the macroscopic world we all live in.
You know, understanding temperature is absolutely fundamental to our lives. It drives our planet's weather and climate. It allows us to cook our food safely and perfectly. We use it to monitor our health and know if we're sick. It's essential for engineering everything from car engines to spacecraft, and it's one of the most critical measurements in pretty much every scientific experiment ever. This brings us right back to the core idea of our entire explainer. This quote from scientist Aurora Lipper just says it all perfectly. Temperature isn't some abstract, weird concept. It's a direct reading of the speed of the molecules that make up our world. So I'll leave you with this thought. We've just revealed that the feeling of hot and cold is really the invisible motion of countless tiny particles. It makes you wonder, doesn't it? If temperature is just motion, what other invisible forces are shaping our world right now, just waiting to be explained?